Tonight's presentation is cam distress, and our presenter is Mike Bush. Mike is the president of Savvy Aircraft Maintenance Management. He holds a certified flight instructor certificate. He's an author for numerous aviation publications, including a monthly column with EAA Sport Aviation magazine. Mike holds an A&P mechanic certificate with inspection authorization and was honored by the FAA in 2008 as the Aviation Maintenance Technician of the Year. Mike's also a member of the EAA. Mike, thank you so much for volunteering your time tonight to be with us. I'm going to turn control of the presentation over to you.
Tonight's presentation, as Tim said, is on the subject of cam distress. I don't want to get too far down in the weeds on this, but this is a very important subject to anybody that operates a piston aircraft engine, because a cam and lifter spalling, and we'll talk about exactly what that is in a moment, is the -- reason that piston aircraft engines fail to make TBO. So if your engine has needs a premature overhaul, dollars to donuts, it's going to be because of a problem with the cam and lifter interface. And what I'm talking about here is the interface between cam lobes on the camshaft and the lifters, or sometimes they're called tappets, that ride on the cam and operate the push rods that open and close the valves in each cylinder. That interface between the tappet and the cam lobe is the highest pressure interface in the entire engine, and it gets probably the worst lubrication of any metal-to-metal interface in the engine, because it's only lubricated by splash oil. There's no pressure oil that goes to that interface. And so in order to make cams and lifters that will go the distance to TBO, the manufacturers spend a lot of time making sure that the metallurgy of that interface is the best it can be. The tappets are normally made of material called chilled cast iron, which is essentially a very low carbon steel that is designed to be tough. Tough is sort of the opposite of hard. It means that it that the material can flex, and it can self-heal small defects in it. The cam lobe, on the other hand, is made of very hard stuff. The camshaft is made of medium carbon steel, and then the entire the cam lobes are case hardened through a process called carburization, where the camshaft, after it's forged and ground and so on, is baked in an oven in a carbon monoxide atmosphere. And so the outer layer of each cam lobe absorbs extra carbon molecules from the carbon monoxide and becomes extremely hard. So the design of this interface is that the cam lobe is hard and the tappet face or lifter face is tough, and that if something starts to go bad with that interface, the lifter will be affected first. So we're talking about the problem of spalling of the cam lifter interface. So let's talk for a minute about what spalling is. The dictionary definition of spalling is a process where fragments of material are ejected from a surface due to stress. And here's an example of a cam lobe that is starting to spall, and you can see little pieces missing if you look at the picture. Here's a close-up of it that makes it a little bit more obvious. And let's talk about why this happens, because in a perfect world, this cam would not spall. The reason it happens is really a two-phase process that leads to spalling. The first stage is that the surface develops tiny corrosion pits, and normally that happens because the engine goes through extended periods of disuse in a moist or corrosive atmosphere. We see a lot more of this problem for airplanes that are based in Florida than we do, say, airplanes based in Denver. And also we see this problem much more in owner-flown airplanes that tend to sit around unflown for long periods of time, and very seldom see it in working airplanes, say an airplane in a flying club or a flight school, or one that carries canceled checks at night. Airplanes that fly every day or at least every week very seldom develop cam and lifter problems. But airplanes that sit unused, in particular ones that sit unflown in a corrosive environment, whether it's Florida or Houston or someplace that's moist and often close to the ocean or close to a lake or something, the protective oil film will gradually strip off the surfaces, and once that happens, the surfaces are exposed to a corrosive atmosphere and can start to corrode and develop these little tiny microscopic corrosion pits like this. Then once these pits develop on the surface due to disuse and corrosion, then when the engine goes back into service and the airplane is flown, the mechanical action of the cam rubbing against the lifter face will start enlarging those microscopic pits until they get big enough that the surface starts shedding significant size pieces of material, typically in the form of flakes or whiskers. We'll take a look at some of the metal that is liberated when this spalling process happens. This is a really neat picture. This is 3 lifters that were removed from a Continental engine, and they're shown in various stages of destruction. The first one looks pretty good unless you look at it very closely, and you can see that there are some scratches on the face of the lifter, probably because some foreign material got into the oil, sand or something like that. Maybe a bad oil filter, maybe a leak in the induction system. And once that surface was disrupted, the mechanical action starts to tear the surface apart. That number 2 lobe, as you can see, is partially spalled, and about, I don't know, maybe 20% of the surface has been destroyed by the spalling process. And that number 3 lifter is in its sort of final state of destruction, where the entire face of the lifter is spalled. And although these are 3 different lifters, you can almost think of this as a time-lapse sequence of what would happen to that number 1 lifter if it stayed in service and it gradually came apart. To understand exactly how this happens, it's helpful to remember that metal is actually a crystalline structure of atoms. In steel, most of the atoms are iron atoms that sit in a lattice structure, and they have a small amount of carbon and some other materials added to the iron. Most of it is iron. But it's a lattice structure if you look at it at the atomic level. And a good way to think about this is, because it's hard to visualize stuff at the atomic level, is to think about a metal surface as if it was a brick wall. And a properly constructed brick wall, as you know, can last for centuries. But once a brick comes out, it exposes its neighbors to attack from the elements. And and before too long, some of the neighbors start falling out, and you start, getting a larger a defect. And when that happens, even more of the neighbors are exposed to the elements. And over a fairly short period of time, that brick wall will start to disintegrate. And that's kind of the mental picture that you should have when you visualize how this happens to a lifter. This is a lifter in obviously a very significant state of spalling, where a large amount of material has come out. So in the real world, you have your airplane in for maintenance. This one happens to be a Cessna 182, and your mechanic pulls the cylinder for some reason. It has low compression or something. And having pulled the cylinder, of course, any self-respecting mechanic is going to go ahead and stick his head in the hole to see what's going on inside the engine, since he just made a big hole in the side of it. So he sticks his head in the hole that was made by removing the cylinder, and he takes a look at the cam and lifters. And typically, removing a cylinder will expose one or two cam lobes to be visually inspected. We take a little closer look at it, and here's what we see. And you can see that the lifter in this engine is in a severely spalled state. We can't see the whole face of it, but it's pretty clear that the entire face of the lifter is severely spalled. But this is a Continental engine, and it's really easy to change lifters. They're what are called barrel style lifters, and you can just remove them from the outside and throw a new lifter in, and then it only takes about maybe an hour and a half of labor to change a lifter on a Continental engine. A lot less than that, obviously, if you've pulled the cylinder. If you pull the cylinder, it only takes a few minutes to change the lifter, and the lifters aren't terribly expensive. They're $80 or something like that. So if we saw a lifter like this, we would definitely want to change it right away. But the question is the cam airworthy? Can the cam remain in service? Because Continental lifters are cheap and easy to replace, but a bad cam is a very big deal. To replace the cam, of course, you have to do a full engine tear down, and you're looking at a minimum of say $10,000 to change out a cam, and often more than that. So to make that decision as to whether the cam is still good, Continental has quite a good service bulletin on the subject. It's called SID 05-1A. It was originally issued in 2005, and it was recently revised. That's what the A after the 1 means. And in a nutshell, and it's got a lot of good pictures in it, and a very textbook approach to evaluating cams and lifters and deciding whether they are okay to remain in service or not. Sort of a summary of the guidance that it gives, it looks like this. It says a lifter that has minor spalling, up to 10% of the lifter face, is acceptable. And they picture a lifter with spalling around the edges, as you can see. I personally don't agree with this guidance. On a Continental engine, it's so easy to change a lifter that if any defects at all are seen in the face of the lifter, I personally would just go ahead and change it. It's not a lot of work. The lifter isn't very expensive, and we want to give the cam the best possible chance of survival. So personally, even if I saw a small amount of spalling on a lifter, like pictured here, I would change it. But Continental's guidance is that spalling of up to 10% of the lifter face is acceptable. I think they probably said that to sort of prevent a lot of warranty claims on minor flaws in lifters. But if the lifter face is spalled more than 10%, then Continental says that the lifter is not acceptable and it needs to be changed. So that's the guidance that they give on that. Now for cam lobes, it's a little bit more complicated. But basically what Continental says about cam lobes is that minor pitting is acceptable so long as it isn't deep enough to catch the tip of a sharp pick. So what they're saying is that if a mechanic sees any pitting on the cam lobe, he should go probe the pitted area with a sharp pick and determine whether those corrosion pits have significant depth to them so that they would catch the tip of the sharp pick. If they don't, then the cam can be continued in service. If they do catch the tip of the sharp pick, then the cam is considered unairworthy and the engine's going to need a tear down. Now again, the logic behind this guidance in the service bulletin, as I mentioned before, is that the way cam lobes are made, they're made with steel that's moderately soft on the inside, but then case hardened through carburizing to create a very hard outer wear surface. And that case hardened outer layer that's created through the carburization is about 15/1000 of an inch thick. So if the surface is pitted, but the pits aren't deep enough to penetrate that carburized, that hardened layer, then the cam lobe is probably okay, and it probably will continue without coming apart. But if the pit gets deep enough to penetrate the carburized layer and get into the softer inner meat of the cam lobe, then that cam lobe is going to come apart. And so the sharp pick test that Continental recommends in their service bulletin is basically a kind of a poor man's way to determine whether corrosion pits are deep enough that they might have penetrated that carburized layer. And that's the logic behind that guidance. So again, here are two cam lobes. The one on the left has some very tiny corrosion pits, but probably not enough to catch the tip of a sharp pick, probably not enough to have penetrated the carburized layer. The one on the right, you can see at least two deeper indentations there that almost certainly would catch the tip of a sharp pick and almost certainly have penetrated that 15/1000 inch thick hardened layer. And so that cam would be considered unairworthy and would need to be replaced. Here's a cam lobe that's in really awful shape with a great deal of material lost, and of course this one is a no-brainer. That engine has to be torn down before further flight. Now, usually the way we get to look at a cam lobe is when a cylinder comes off, as I recall. I'm just getting ahead of myself for a second. Here are some other pictures that came out of the Continental Service Bulletin showing normal wear signatures on a cam. This is what a cam that's been in service for a while should look like. And you can see the wear surfaces are shiny, and they tend to be a little bit scalloped because of the way the lifter contacts various areas of the cam as it rotates. But these are showing kind of shiny wear patterns that aren't exhibiting any significant pitting, and these cam lobes, just it shows the lobe in different positions of rotation, are all in healthy shape. As I said, most of the time when we look at a cam lobe, it's because a cylinder got pulled and we have a chance to stick our head in the hole and take a look. But at least on Continental engines where they have these lifters that can be pulled from the outside, if you want to, you can get a pretty good look at the cam just by pulling the lifter and looking through the vacant lifter boss, which the hole in the crankshaft, I mean the hole in the crankcase that was occupied by the lifter and is now vacant. And nowadays we can stick bore scope into the lifter boss and get really good photographs of the cam. So if there's some question about what the cam looks like, let's say some metal got found in the oil filter and you wonder whether it was coming from a cam, you don't need to pull a cylinder. You can pull lifters, which is a whole lot quicker, and look at the cam through the lifter boss, and even with a bore scope take pictures. Now so far I've been talking about Continentals because they're the easier of the engines to deal with. How about Lycomings? Well, Lycomings are tougher with respect to cam and lifter problems, and they're tougher for two reasons. First of all, Lycoming engines, by the virtue of how they're designed, suffer more frequent cam and lifter problems than Continentals do. And it's because of the configuration of the engine. Continental engines have a low-mounted camshaft that's mounted below the crankshaft. Lycoming engines are reversed. They have a high-mounted camshaft that's mounted above the crankshaft. So when oil starts to extrude from the main bearings as you're first starting an engine, in the case of a Continental, gravity takes that oil downwards, and it normally falls right on the camshaft. So the camshaft gets lubricated very early in the start cycle. And when the airplane is shut down at the end of a flight, there's probably a half a quart of oil adhered to the crankshaft, and over time that oil gradually drips off and it drips right onto the cam. So the cam continues to have its oil film augmented for a fairly significant period of time. In the case of Lycomings, where the camshaft is above the crankshaft, gravity doesn't help the cam at all. It hurts the cam. On start, the camshaft doesn't really get any lubrication until the crankshaft is spinning fast enough to start flinging oil up towards the top of the crankcase where the cam is. And on shutdown, the cam, being the highest thing inside the crankcase, loses its oil film first before anything else. And so as a result of the high-mounted cam, Lycomings are more vulnerable to cam and lifter spalling, and so owners have to be a lot more attentive. The second significant thing about Lycomings that makes this difficult is that, unlike Continentals that use barrel-style lifters, Lycoming engines use mushroom-style lifters, like the picture on this slide, so that the tappet face of the lifter is much larger than the body of the lifter. And as a result, you can't remove a Lycoming lifter from the outside of the engine. If a lifter gets in trouble on a Lycoming, the only way to replace it is to split the case. So on Continentals, cam problems are a very big expensive deal, but lifter problems are cheap and easy to fix. On Lycomings, both lifter and cam problems involve tearing down the engine. So the consequences of a lifter problem on a Lycoming are much more expensive for that reason. Here are some pictures inside a Lycoming. This one has a cylinder removed, and you can see that the cam is in pretty bad shape. There's a bunch of nasty things on the toe of the cam, and clearly that cam is going to have to be replaced. You can also see this one. This happens to be an intake lobe that is operating two opposing intake valves. So there's two tappets, one on each side, in contact with this one cam lobe. We tend to see the intake lobes fail first, again because they're driving they're driving two lifters. They're being shared between two cylinders, whereas the exhaust lobes drive only a single exhaust valve, and only a single tappet is in contact with it. But at any rate, this cam is obviously toast. And you can also see the two lifter faces, and you can see how large they are. They're much larger than Continentals. And because they're so large, you can't remove the lifter from the outside. It's the tappet face is much larger than the hole in the case, and so the only way to remove the lifters is to split the case. Here's another picture showing a Lycoming lifter. Again, you can see how huge it is. This is an exhaust lobe. There's only one tappet in contact with it, and that tappet is in a very severe case of full face spalling. And again, because this is a Lycoming, the engine's going to have to get torn down to resolve that problem. Here's another one, and actually the small bit of the cam lobe that we can see at the left side of this picture really doesn't look in too bad shape, but the lifter looks in very bad shape. And again, because it's a Lycoming, we can't change that lifter in the field. We have to send the engine in for teardown. So we don't like to see that happen. Sometimes we find out about a cam and lifter spalling not by pulling a cylinder, but by finding metal in the oil filter. Normally it would be ferrous metal, so it would adhere to a magnet, and it normally is in the form of either flakes or whiskers. If the metal is whisker shaped, like this metal that's shown here, and if it sticks to a magnet, it's very, very likely that it came from a spalled lifter, because that's how the metal tends to come off of lifters, kind of in whisker form. Let's see, here's a picture of some whiskers from an oil filter adhered to a mechanic's magnet. The tip of that magnet is a 1/4 inch in diameter, to give you a kind of a scale on this thing. But those things are clearly in whisker shape and clearly magnetic, and that's usually pretty bad news. It means that a lifter's coming apart. Particularly bad news if it's a Lycoming. And here's another example of some ferrous metal whiskers adhered to a magnet. So how are we going to prevent this kind of thing from happening? And those of you who fly Lycomings, you are particularly incentivized to try to prevent these problems, because they're very, very expensive to resolve. Well, I've already mentioned that airplanes that fly regularly, say once a week or more often than that, almost never suffer cam and lifter problems, because the oil film just never gets a chance to strip off the cam and lifters. They don't get a chance to be exposed to a corrosive atmosphere, and so the problem doesn't happen. These problems are mostly with owner-flown airplanes that fly irregularly. They're worst with airplanes that live in a very corrosive environment, like the Gulf Coast or Florida or something like that, and also airplanes that fly seasonally, that sit unflown for months at a time during the winter, for example, where corrosion has a chance to take hold on these parts. We want to change our oil regularly to prevent a buildup of acids and other corrosives in the oil that will corrosively attack these expensive components. We recommend changing the oil no more than once every 50 hours or once every 4 months, whichever comes first. That assumes you have a full flow oil filter. If you only have a screen, you want to change it more often than that. If you fly in dirty conditions, like say flying off of dirt runways and stuff like that. You want to change it more often than that. If the airplane's going to sit unflown for a little while, it's better to change the oil before the period of disuse than after, so that while the airplane is sitting there unflown, the parts are coated with nice clean oil. If you know that the engine is going to be unflown for say a month or more, let's say you're taking the family to Europe or something like that, it's a really good idea to pickle the engine, to put it in preservative storage. I went through the details of exactly how to do that in another webinar, but basically it's a glorified oil change with a special anti-rust oil and some desiccant plugs to make sure that all of the moisture gets removed from the engine. And if you go onto Aircraft Spruce and search for a pickle kit, you'll find that they sell a little kit of materials, the oil and the desiccant stuff, everything you need to pickle an engine, and it's a preventive maintenance thing. It's something an owner can do himself. We want to use, particularly if you're operating in a corrosive environment, we want to use anti-rust and anti-scuff oil additives. And let me wrap up this discussion by talking a little bit about these additives. Some of the aviation oils, well, first of all, Lycoming sells an anti-scuff additive with the charming name of LW16702. Trips off the tongue, and it's basically triphenyl phosphate, which is an anti-scuff additive. And there's actually on a few Lycoming engines, notably the 0320 H2AD engine that was used in the Cessna 172 for a few years, that has a particularly terrible history of cam and lifter spalling. There's actually an AD requiring that this additive be added to the oil. There are several aviation oils that have that triphenyl phosphate, that the same stuff as is in that Lycoming additive, pre-blended in, including Aeroshell 15W50, Aeroshell W100 Plus, and Exxon Elite 20W50. Those all have triphenyl phosphate pre-blended into the oil. I won't get into a big discussion on oil. I personally do not like Aeroshell 15W50. It's the one oil I recommend people not use, and I have a all about oil webinar that gets into more detail about why I don't like it. But these three oils do have anti-scuff and anti-rust additives pre-blended in. My own personal favorite is an additive, and the one I use in my own airplane, and that we use in most of the 600 or so airplanes that my company manages the maintenance of, is called CamGuard, and I think it has the best set of the best additive package for preserving the cam and lifter interface, both anti-rust, anti-corrosion, and anti-scuff additives. Anti-corrosion means prevents corrosion of aluminum parts. Anti-rust means it prevents corrosion of iron and steel parts. And anti-scuff means that it helps prevent the cam and lifter interface from wearing during the start cycle after the airplane's been sitting for a while and the oil film has stripped off. And so this is the additive that I use in my own engine. And incidentally, I'm in the process of tearing down one of the engines on my 310 finally. It's at 205% of TBO, and we pulled all the cylinders off and inspected all the lobes of the cam, and the cam and lifters are pristine after let's see, 25 years, and well over 3,000 hours. So camguard has obviously been doing a very good job on that engine. So it's the stuff that I use and that I recommend to our managed maintenance clients. Tim, that's all I have. So we've got some time for Q&A.
Fantastic. Yeah, we had a few questions scream in here as you were talking, so let's start in with those. Stephen's just wondering, can you distinguish whether you have a cam or lifter problem from an oil analysis?
Actually not. Interestingly enough, in almost every case that I've seen where a cam or lifter is coming apart, the oil analysis reports look absolutely normal. And the reason for that is that when a cam and lifter starts coming apart, when the spalling happens, it's liberating fairly large pieces of material off the surfaces. And that material is caught by the oil filter. And so, since it's caught by the oil filter, it never gets into the oil sample jar. And so the oil lab doesn't see it. Oil analysis is great for detecting very slow wear events that throw off microscopic particles. Let's say accelerated wear of an exhaust valve guide or a valve stem or something like that. But it's not good at detecting rapid wear events that throw off large metal particles that are big enough to be caught by the oil filter, and the oil filter will catch particles down to about 20 microns in diameter. And so particles that are larger than 20 microns typically don't wind up in the sample jar and are invisible to oil analysis. So the shorter answer is no, oil analysis typically will not tip you off to a cam and lifter problem, at least in my experience.
All right. Walt is wondering, can a new lifter be mated to an old camshaft, or does the camshaft need some kind of surface treatment?
No, a new lifter is we put in new lifters all the time, and they, as I said, the lifter is relatively soft and conformal, and it breaks into the cam shape pretty rapidly. When an engine is first built up during overhaul or reassembly, typically they put some sort of a break-in lubricant on the lobe, like molybdenum grease, and it probably would not be a bad idea to do that when changing a lifter on a Continental engine. We could put a little dab of it through the lifter bore before installing the lifter. But no, the lifter will conform to the cam. You definitely can put a new lifter in with a worn cam lobe, and that's done all the time.
David's wondering, is that Continental service bulletin available?
Sure, it's online. Just if you go to Google and Google SID 05-1A, it'll take you right to the PDF. In fact, that's what I was doing yesterday when I made up the slide. So I know it works.
Does Lycoming have a document similar?
Not that I can find. I've not found a service bulletin from Lycoming regarding the evaluation of spalled cams and lifters.
And Jim's wondering, why hasn't Continental gone to roller lifters?
Well, as I said, Continentals typically don't have this problem nearly as often as Lycoming's because of the basic design of the engine with the low-mounted cam. the cam gets much better lubrication in a Continental than it does in a Lycoming. And so Lycoming just has a much bigger problem, and of course their latest approach to trying to deal with it is roller lifters, which are what are being shipped with the new generation of Lycoming engines. But Continental hasn't changed that simply because the problem is much rarer with Continentals, and also again with the Continental design, if the lifter starts to spall and you catch it before the cam gets damaged too badly, you can just pull the lifter out and throw a new one in, and the Lycoming can't do that.
Are the new Lycoming roller lifters, would it still be wise to use something like camguard or an oil with the additive in there?
I think it would. I have to confess that the roller lifters Lycomings have not really been in the field long enough for me to have any strong feelings about how they're holding up and so on. There aren't all that many roller lifter Lycomings that are at TBO yet, and so we'll know more about that in a few more years. But yes, if I had a Lycoming with roller lifters, I would definitely, and particularly if I was based in a corrosive environment, I would definitely go ahead and use camguard or LW 17602 or one of the oils that has that stuff pre-blended into it. Personally, I would use camguard because I think it's the best package available right now.
Walt's wondering, are the lifters normally a solid or are they hydraulic?
All the engines I've ever seen, that are flat engines, use hydraulic lifters. The radial engines use solid tappets, but and don't ask me too many questions about radials because I don't have much experience working on them. But all of the flat engines that I've ever seen use hydraulic lifters.
James is wondering, why aren't cams and lifters pressure sprayed with engine oil? Is temperature too high or some other reason?
Well, it's a good question. There is an STC available from a company called Firewall Forward in Colorado for a cam that has it has a hollow. It's hollow inside, has an oil passage inside, and has a little hole drilled in the toe of each cam lobe so that pressurized oil is extruded onto the toe of the cam lobe. There are so few engines with that STC cam that I would not want to venture an opinion as to whether that STC is a good one. There's also some engines have what are called oil squirts, which are basically little roll pins that are inserted into the crankcase halves into the main oil gallery and squirt oil kind of in the direction of the camshaft. And for engines that are not equipped with those squirts, there's an STC for modifying the engine to install the squirts. So there have been various attempts to solve this problem, but again, the real anything you do like that only benefits the cam when the engine is running, and the root of this problem is really the periods of time when the engine is dormant. and the protective oil film strips off of the cam and lifters and exposes it to corrosive attack. So to really solve this problem, either you've got to fly the airplane regularly, or you've got to deal with the corrosion issue in some way. And anti-rust additives try to deal with that. Hangering the airplane obviously helps. Living in a dry climate obviously helps a great deal. But that's really what that's really how the problem has to be dealt with. It's really a problem that starts with corrosion, and so you have to figure out a way to stop the corrosion.
Keith is wondering, if you can't fly, is it better to start the engine and run it on the ground but not get the oil up to 180 degrees, or is it better to just leave the engine alone?
You know, that's a really tough one. The running the engine on the ground, it's a two-edged sword. On one hand, it reestablishes an oil film, and on the other hand, see, every time you shut the engine down, a large bolus of water gets added to the engine oil, and the only way that water gets removed is to get the oil temperature up high enough that the water turns into steam and is expelled out the breather. And typically that only happens when you actually fly the airplane. So it's really a very much a good news bad news story, just running the engine on the ground. That's why, if you know the airplane's going to be inactive for a while, the best thing you can do is pickle the engine, which is not a very difficult or expensive process. It simply involves putting a special preservative oil in the engine, running the engine for a while to get it distributed, and then pulling the top spark plugs and putting plastic desiccant plugs in their place to absorb any moisture that's still in the cylinders, and putting some bags of desiccant material in the exhaust and intake to absorb any moisture in those systems. And if you pickle the engine in that fashion, then you can let it sit for 6 months and nothing bad's going to happen, because you basically put a preservative oil over everything, which sticks like glue, and removed as much moisture as it's possible to remove. So that's the best thing to do if you know that the airplane's going to be inactive for over a month or so.
Gary's just got a question here about cam spalling prevention. He says he flies behind a Lycoming 0360 with an engine heater that heats the oil pan and individual cylinders, a Tanis heater. Mm-hmm. Is it better to leave it plugged in all the time or only prior to flight? Or does it matter that much? I've heard that the thinking to only preheat before the flight, if it's regularly flowing, to prevent moisture and condensation.
Tanis did a really interesting study on that subject some years back, and they wrote a very interesting white paper, which at one point was on the Tanis website. I don't know if it's still there or not. It's been years since I looked at it. But basically their conclusion was that it is a good thing to run the heater continuously if you also hook the engine up to a dehydrator. Tanis makes one, or at least they used to make one, and several other companies make them, and you can go to Spruce and find several of them. They're usually, I don't know, $150 or $200. But the engine dehydrator is basically a small air pump that pumps air through a chamber of desiccant crystals, and then is hooked through a tube to the engine's crankcase vent. And the idea is that it continuously pumps a small volume of almost perfectly dry air into the engine, and that displaces any moist air that's in the engine. And if you do that, if you run a dehydrator, then you can run the Tanis heater 24/7, and it'll keep the engine dry and corrosion free. However, if you run the heater and don't run the dehydrator, what Tanis found was that the heater will vaporize moisture in the engine, and then that moisture will condense on whatever is coldest in the engine. For example, the gear train at the back of the engine, the crankshaft and crankcase gears. I know in Continental engines, the worst problem happens with the starter adapter, which is the gizmo, the clutch kind of gizmo that connects the starter to the crankshaft. And so the moisture will wind up condensing on some cold component and just turn it into a massive rust. And so the bottom line is that Tanis's recommendation was, if you aren't using an engine dehydrator that forces desiccant dried air into the engine, then it's not a good idea to run the heater continuously. It should only be run turned on, a few hours before you plan to depart on a flight in cold weather.
Excellent. Francis is wondering, do excessively worn cam lobes result in a loss of horsepower?
Well, in theory they do. In practice, it's amazing. We've seen cam lobes that were worn so badly that you could hardly tell where the toe of the lobe was, and the pilot never noticed any loss of performance. So I would say that that a worn cam lobe does result in a small loss of horsepower, and probably, if it's just one lobe that's worn, it would probably also result in a slight increase in engine roughness because one cylinder wasn't making the same amount of power as other cylinders. But the effect is so subtle that it's very unusual for it to even be noticeable.
Walt is wondering, are engine pre-oilers a useful option to pre-lube the engine to reduce wear?
Well, they're useful, but not as useful as you might think, because what a pre-oiler does, it pressurizes the oil system before you start the engine, of course. And so what does that do? It provides early lubrication to everything in the engine that's pressure lubricated, bearings and stuff like that. But we never have a problem with the pressure lubricated parts. And what a pre-oiler doesn't do is it doesn't provide splash oil. So, for example, it doesn't get oil. It won't get oil to the cam of a Lycoming. I suppose if the Lycoming was one that had oil squirts, then maybe it would get a little bit of oil to the cam lobe. In Continental engines, it actually does get oil to the cam lobe, because the oil that's pumped into the main and rod bearings wind up being extruded out the side of those bearings and falling down into the sump. And as they fall down, they're falling on the low-mounted cam. In Lycomings, which are the engines where we worry about this the most, you can pressurize the oil system all you want, and normally the cam just doesn't get any lubrication at all unless the crankshaft is spinning. So the bottom line is that pre-oilers are helpful, but they're definitely not a panacea, and particularly for Lycoming engines, they won't solve this cam and lifter problem, because they don't have the ability to get oil up to that cam and lifter at the very top of the crankcase.
Sean's wondering, when would you have a camshaft ground, and do they typically reharden the camshaft after grinding?
Yes, if a camshaft is in good shape, it can be reground, and when it's reground, it should always be recarburized. That's part of the process. And there are a few companies that specialize in doing that sort of thing. I actually have reground camshafts in my two engines, and like I said, they went the distance, or they went well more than the distance. So a well done reground camshaft, I think, can be considered to be just as good as a new one if the company that does the regrinding and rehardening does a competent job.
Terry wonders, why does my exhaust smell different when I use ASL camguard?
I've had that question asked to me before. I personally have never noticed the smell, but there are some people who are sensitive to it, and I have not a clue what it is you guys are smelling. All I know is I've never smelled anything funny with camguard, so my nose must be defective somehow.
Henry is asking, looking to possibly buy an aircraft that has been sitting for 15 years, 200 hours since major overhaul, and it was not pickled. Mechanic says he must overhaul because cam must be bad. Is this a for sure thing? Cam shot need to overhaul? Is there anything I can do before starting? What if I just run it and see what happens?
Well, I actually agree with our attendee here and disagree with the mechanic. The thing that's important to understand about cam and lifter spalling is that it is not a safety of flight item. As I said, even a very badly worn cam lobe will hardly make any noticeable difference in engine performance. Nobody ever fell out of the sky because they had a worn cam and lifter. Cam and lifter problems are very much a safety of wallet item, but they aren't a safety of flight item. So personally, I see no downside whatsoever in flying the engine, checking the oil filter carefully to make sure it's not making ferrous metal, and letting the cam and lifter decide whether there's a problem, because I just don't see any safety issue there. I personally wouldn't get heroic and start pulling cylinders and even inspecting the cam, because either the cam is going to be okay, or it's not going to be okay, and the engine's going to start making metal, and you'll know in the fullness of time. But there's really not any safety issue involved, as long as you're watching the oil filter on a regular basis and not letting things come apart, to an extreme extent. So and in fact, that's kind of what Continental hints at in their service bulletin. That it basically says, when you're inspecting the cam lobe, if it's right on the edge of and you can't quite decide whether it's airworthy or not, just throw a new lifter in there, fly it for 100 hours or 12 months, whichever comes first, and then pull the lifter out and see what it looks like. If the lifter still looks good, then you dodged the bullet and you're good to go. If the lifter is torn up after 100 hours or 12 months, then the engine's going to have to get torn down and have a cam transplant. So I know that's a Continental service bullet, and it doesn't really apply to Lycomings officially, but it makes all the sense in the world to me, and that's how I would approach it if it was my airplane. Obviously, it makes a huge difference where the airplane has been sitting for 15 years. If it was sitting for 15 years in Tucson, I would be pretty optimistic. it was sitting for 15 years in Key West, uh, then the engine's almost certainly going to be trash. Um, so there's a lot of factors involved, but I don't see any problem with just flying the engine and letting it, and just seeing whether it starts making metal or not, seeing whether the cam's okay or not that way.
A few questions here about when to add camguard. Can you add it any time, or does it have to be during an oil change? And can you add it at any time during the life of the engine?
Yeah, I mean normally it's put in when you change the oil, but you can add it any time. The concentration that's recommended is 5%. So the stuff comes in little pint containers, and 1 pint treats 10 quarts of oil. And some people will put a little bit of camguard in each quart of makeup oil that they carry around. You know, when you take the top off of a bottle of oil, there's a little airspace in the top, and some people will fill that airspace with a little bit of camguard, so that when you add a quart of makeup oil, it adds a little camguard with it. And certainly there's no problem with adding camguard, you know, starting camguard on an engine that's halfway to TBO. Well, we do that all the time. Occasionally we'll find that if you start camguard on an engine that's got quite a few hours on it, the first oil sample or two will the oil analysis will look pretty funky, because the camguard liberated a bunch of deposit buildup into the oil, and cleaned up the engine. So if the first oil analysis after you start camguard looks a little weird, don't worry about it. That's kind of expected. But yeah, we start airplanes on camguard midway through their TBO on a regular basis. When a client signs up for our managed maintenance service, we find out what kind of oil he's using, and if he's not using an corrosive anti-scuff oil, and he's not using camguard, we'll typically recommend that he start using camguard, especially if he's in a corrosive environment, along the coast or something like that.
Mike's wondering, once whiskers are found in the filter, is there any way to determine which lifter is the problem without inspecting all of them?
Well, there's no way to figure out which lifter it is without inspecting some of them. Obviously, if it's a Continental engine, you can start pulling lifters, and maybe you'll get lucky and the first one you pull is the culprit, or maybe you'll be really unlucky and it'll be the sixth one you pull, or maybe on the average it'll be the third or fourth. So you may not have to pull all the lifters, but there's really no way to determine which lifter is bad without actually being able to lay eyes on the lifter. But as I said, with Continental engines, it's pretty painless to pull the lifter and inspect it. We normally figure about an hour and a half labor per cylinder to pull both lifters associated with a particular cylinder. And we normally don't pull lifters in routine maintenance, but we very frequently pull lifters during a pre-buy. And that's something that we do if we think the engine is at risk because it's been inactive for a while before the pre-buy, and it's been living in a bad place. Then we'll normally recommend that the lifters be pulled, or at least half of them be pulled during a pre-buy, and to see what the condition of the lifters in the cam are. And again, that's in Continental engines. Obviously, in Lycomings, you don't have the option of doing that.
Noel was wondering, other than disuse, are there engine operation habits, such as power settings, starting behavior, etc., that can exacerbate, I'm sorry, I butchered that,
Exacerbate.
exacerbate, thank you.
You're welcome.
Man, that didn't want to come out. Okay, what else can exacerbate spalling or cam and lifter wear?
Well, anything that causes the oil to be more corrosive than it should be, that would include, for example, running the engine excessively rich. It would include over-priming the engine in cold weather and dumping a bunch of raw fuel into the crankcase because the fuel breaks down into free radicals. It can be quite corrosive to the engine parts. So anything like that. Oil analysis will frequently tell you whether the oil is more that you've drained at the oil change interval is more corrosive than it should be. But yeah, there are a few things in addition to simply periods of disuse that can aggravate the situation. Over-priming is one of the most common that we see, especially for airplanes that live in cold climates. You only want to prime just as much as you need to get the engine started, and a little extra actually is harmful because it falls into the crankcase and makes the oil nasty.
Ray just wonders, car engines don't seem to have problems with lifters like aircraft engines. Why not?
Because we typically drive them every day. That's the big difference between car engines and aircraft engines. Well, one of the big differences is that it's very seldom that you would go for a week or more without driving your car, at least for most people. But it's very frequent that people go for weeks at a time, sometimes even months at a time, without flying an airplane. And so the disuse is just a much bigger problem for airplanes.
Roger's wondering if you got an estimate of what percentage of owner-flown engines end up with cam and lifter problems that necessitate a teardown.
That would be a very interesting number to have. I don't know how to go about getting that information, and so I really can't answer the question. But we do see it with uncomfortable frequency, and again, we see it a lot more with airplanes that live in humid climates. We see it a lot more with Lycomings than we do with Continentals, and again, we almost never see it with working airplanes that fly regularly once a week or more often than that.
So John's wondering, what about AvBlend versus camguard for engine protection?
AvBlend does not have, is not an anti-corrosive, does not purport to be an anti-corrosive, in fact. And back when AvBlend first came out, AvBlend is actually just a repackaging of an automobile additive called Lenkite that's been on the market for decades, and they repackaged it and called it AvBlend for the aviation market. And when it was first introduced, and this has got to be, I don't know, 25 years ago maybe, we actually ran a test of it in a couple of twin-engine airplanes where we would treat one engine and not the other, and then we'd do oil analysis on the engines at every oil change. This test was done in conjunction with Howard Fenton, who ran what at that time was the leading aviation oil analysis lab. And to be honest, we could never tell the difference between the treated engine and the untreated engine. So I've never actually seen any hard evidence suggesting that AvBlend is helpful. I've also never seen any evidence that it's harmful, so I don't discourage people from using it if it makes them, feel warm and fuzzy. But I've just personally never seen any indication that AvBlend is helpful. I don't use it, and I don't recommend it to my clients particularly. I mean, I don't disrecommend it. I just don't talk about it.
John's wondering, is there really truth in not using magnets to remove lifters?
Goodness. I've never heard of anybody using magnet to remove lifters. We always just stick the end of a sharp pick in the oil hole and cock it a little bit and slide the lifter out. I don't know. This is the first time anybody's ever even proposed the idea of using a magnet. In general, it's not a good idea to use magnets on engine parts because you really don't want to magnetize anything in an engine. But that's a new one on me. I didn't know anybody was using magnets to remove lifters. I've never seen anybody do it, and I've never done that myself.
And Greg's wondering about the Lycoming lifters. Is there any advantage to the Lycoming mushroom style lifter over the Continental?
Well, there is. The surface of the Lycoming lifter is very large, and if you take a look at those severely spalled lifters in the Continental pictures that I had up, you'll notice that the spalling doesn't reach the very edge of the lifter face. That there's actually a little margin around the lifter face that isn't in contact with the cam, whereas the Continental lifters don't completely cover the cam lobe, and the edges of the Continental lifters, which are considerably smaller in diameter, when a lifter starts coming apart, they actually start getting I don't know what you'd say, but metal is actually starts kind of being shoved off the edge of the lifter face, and a really badly spalled lifter sometimes is hard to extract from the crankcase because the face of the Continental lifter is almost like it's peened over on the edges. So there's an advantage to having a large lifter face in terms of lifter longevity, but the disadvantage is that if the lifter goes bad, you can't change it in the field. And now Lycoming, in all fairness, tried to use the barrel style lifters in that 0320 H2AD that was that they made for Cessna for I don't know 5 years or so, and that used barrel style lifters much like a Continental. They're the only Lycomings I know of that did use barrel style lifters, and they worked okay up in the northern part of the U.S., but they had a really bad track record but down in the southern part of the U.S. where the corrosion problem is worse. And so Lycoming, the Cessna stopped using the H2AD variant and went back to a mushroom style Lycoming engine. And most of the 172s in the field that had the H2AD engine have now gone through overhaul and been converted to mushroom style lifters. It just didn't work very well for them. Again, the Lycoming cam, because it's mounted up high and it's not lubricated nearly as well, it just is just more problematic to make those lifters last.
A few questions here from folks about using Marvel Mystery Oil. Any comment on that as it relates to the cam?
Marvel Mystery Oil will have no effect on cam and lifter spalling. It's not an anti-corrosive. It's not an anti-scuff. It's basically Marble Mystery Oil is a pretty good solvent, and there is some pretty good anecdotal evidence that it is helpful in freeing up stuck hydraulic lifters. If you start hearing lifter clatter, I've actually been known to look both ways, make sure there aren't any FAA people around, and then surreptitiously dump a quart of Marble Mystery Oil in my crankcase if I think I'm hearing a lifter starting to clatter. But the Marble Mystery Oil would not have any effect on cam and lifter spalling. It doesn't address that issue at all. It's basically a solvent, petroleum distillate solvent with some red food coloring and a little perfume added to it. And it's not a mystery anymore, because now you can go on the internet and pull up the MSDS sheet on Marble Mystery Oil and see exactly what's in it.
Roger says, my mechanic has suggested replacing push rod tube seals at next annual. Is that an opportune time to also check the lifters on my 0470?
Oh, absolutely. If you're replacing the push rod seals, it would be criminal not to pull the lifter, because it would only take an extra 5 minutes to pull and inspect the lifter and to put a flashlight into the empty lifter boss and take a look at the cam lobes. You definitely will want to inspect the lifters and even the cam lobe when you're replacing pushrod tube seals. And those things do tend to start leaking on Continentals after a while. But anytime you change the pushrod housing seals, you're basically exposing the lifter, and you can just pull it out and look at it, and it would be crazy not to do that. And I'm sure your mechanic would do that.
Paul's wondering, if you pull one lifter on a Continental, would you be able to inspect all the other lifters and cam lobes by using a bore scope?
No way. Basically, the crankcase is partitioned up into cells, kind of, by the main bearing saddles, and you can't really see next door with a bore scope by pulling one lifter. There's no possibility of doing that. It's just physically not possible.
Keith's wondering, are desiccant dryers that pump air through the dipstick useful year-round if you're living in a corrosive environment?
You betcha. Absolutely.
Marlon's wondering, on a new engine, would you add the camguard to the mineral oil during break-in?
No, I wouldn't use camguard during break-in. It's got anti-scuff additives, and basically break-in is a time when you're intentionally scuffing, if you will. So you don't want to use, for break-in, you don't want to use any oil that has anti-scuff additives, and you don't want to use any oil that has synthetics in it for break-in. I would, on a new engine, I would start the camguard no earlier than maybe 50 hours.
Richard's wondering, does pulling the dipstick partially out after shutdown to allow moisture to escape the crankcase help?
It helps a little. It does help a little. The problem is, if you do that, you better remember to put it back in before you go fly the airplane. So if you do that, it's a really good idea to put some kind of a red streamer or something in the oil filler door, so you don't forget that you've left the thing ajar. Otherwise, it will make a very big mess. But yeah, it helps a little bit. It's not a bad habit to get into.
Kirk wonders, what about if you turn the prop over, say, once a week if you're not able to fly the aircraft for extended periods? Would this help the cam and tappets?
No, it actually makes things worse. I don't know where that idea came from, that it's a good idea to hand rotate the prop periodically, but it just accelerates the process of stripping oil off the parts, and it's not a good idea. It's something that you should not do. It's better not to turn the prop unless you're about to go flying, or unless you have to turn the prop because you're doing maintenance that requires positioning the crankshaft a certain position, say timing the mags or something like that.
And David's just making a comment here about the Lycoming engine, if there's a bulletin out there. He says there's a service instruction number 1011K, K as in kilo, for lifter evaluation at overhaul. Might be helpful.
Okay, 1011K. I'll look at that. Obviously, you know, they say lifter evaluation at overhaul because you basically can't do anything about a lifter in Lycoming except when you've got the engine torn apart.
Merrick's just wondering if you have any experience, have new versus reground cams survived better?
Well, as I said, I have reground cams in my engines. They've done great. A reground cam done by a good, competent regrinding shop is going to be just as good as a new cam. Also, we've got a lot of experience with reground lifters because there've been a couple of times, one not very long ago, maybe a year or two ago, where, for example, Continental got a big batch of defective lifters from their lifter vendor, and suddenly they were out of lifters, and in order not to shut the factory down completely for 2 weeks, they started shipping new engines with reground lifters, and they actually had to get special permission from the FAA to do that, because normally a new engine is supposed to have new everything in it. But reground lifters, again, done by a competent shop like Aircraft Specialty Services in Oak City, are just as good as new lifters.
Peter's wondering, if a spalled lifter is not replaced, what is the ultimate failure like? Does the engine eventually come apart?
No, basically if the spalled lifter isn't replaced, the cam lobe's going to start getting torn up, and then you're going to wind up with a bunch of metal in the oil filter. I suppose that if that process went far enough, and you say weren't checking your oil filter, or the fact that it had ferrous metal in it didn't bother you, that eventually it could start throwing off so much metal that it might clog the oil filter and put it in bypass, and then the metal could get into the oil galleries and contaminate the bearings, and then you'd have a big problem. But to get that far would require flagrant neglect. So as long as you're cutting open the oil filter at every oil change and inspecting it, I don't think a cam and lifter issue is ever going to get to the point where the engine is in safety of flight jeopardy. That's what I was saying before.
Gotcha. We've had a number of people ask about your engine, Mike, and wondering if you'd care to comment about why you had to take your engine off.
Sure. Actually, I'm going to be writing an article on it for Sport Aviation, but I'm sort of waiting for the final verdict on everything to come in. I had a problem with my airplane. I was actually flying up to AirVenture 2014, and I had a problem with the right engine that caused me to decide to shut it down, feather the prop, and land it at North Las Vegas. And it turned out that what happened was that a the piston, the number 6 piston skirt from the oil control, the scraper ring groove down to the bottom, about half of it just fractured and departed the piston. And it had a big fight with the crankshaft. The crankshaft won, the piston skirt lost, and there were, a whole bunch of aluminum pellets scattered in the crankcase. The piston right now is at the manufacturer. It was an ECI piston that was installed in 1990, about 3,200 hours ago, and they're actually doing a microscopic analysis of the fracture face to try to figure out why that piston failed. It's a very unusual failure. Those pistons that I used are actually unusually strong pistons because they're forged pistons. The pistons that are used today in Continental engines are cast pistons, which aren't nearly as strong. And so we're all very surprised that piston skirt failed. We don't know why it failed. It's a very unusual failure. We're in the process of doing a forensic analysis on the piston to try to figure out what made it fail. But that's pretty much all I can tell you. We're also, we pulled all the connecting rods and are having the rod bearings analyzed to see whether there was any contamination in the oil galleries. If the rod bearings are contaminated, then we have to assume the main bearings are contaminated and the engine will have to be torn down. And we're in the process of trying to make that decision. Hopefully we'll have that decision made within the next week, and I'll know whether we're going to build up the engine without splitting the case or whether we're going to have to split the case. And if I was a betting man, I would guess we're going to split the case on it.
Well, great. Thanks for that information. Good luck with it. Look forward to reading the article when it gets published about your experiences. Looks like we've run up against the end here. It's 9:32. So any closing comments you'd like to make to the crowd? We had a nice audience tonight. My counter showed, I think, close to about 600 people. So
cool.
Good.
That's great.
Good webinar, yeah. Mm-hmm.
Well, I guess just a quick run through on the next first Wednesday of the month webinars that I'm going to be doing. The next one is on April 1st, which is April Fool's Day. So it might not be on that topic at all, whatever I decide. Right. But at least the scheduled subject is the decision point, and it's going to be about how owners need to work with their IAs during annual inspection, and at what point the owner needs to sort of get into the decision loop to sort of keep control of what's going on with the maintenance. The May one is going to be on the subject of engine teardowns and how we decide whether it's necessary to tear down an engine or not. What I was talking about with my engine is we're actually going through that process right now of deciding whether the engine needs to be torn down or not. But we're going to be talking about how we work through the data when we have an engine problem to decide whether or not it needs to be torn down. And then the June one is safe versus airworthy, and it discusses, we often use airworthy as if it's synonymous with safe, but it really isn't. The two words have different meanings, and sometimes an airplane can be safe but not airworthy, and sometimes it can be airworthy but possibly not safe. So we're going to talk about how we decide whether an airplane is safe to fly, how we decide whether an airplane is airworthy, and that's going to be the subject of the June webinar. And finally, as usual, if I encourage people who like to follow the stuff I write and so on to subscribe to my monthly e-newsletter. You can do that two ways. You can do it by going to the SavvyAviator.com website, or you can do it by checking a box on the survey that Tim is going to put up at the end of this webinar. And also, if you haven't already done so, I would encourage you to check out my book on Amazon. It's called Manifesto. If you go and search for Mike Bush Manifesto, it'll take you right there. And again, if you enjoy my stuff, I think you'll enjoy the book. So that's all I have, Tim, and I thank everybody for coming. It's great that we had such a good turnout.
Thank you very much, Mike, for an excellent webinar. This is most informative. Thank you so much. And we got a lot of comments from the audience. Excellent webinar. Thank you so much. And Richard even said, Manifesto is great. I just finished it. The book is awesome.
Well, thank you.
Well, with that, Mike, thank you so much for volunteering, sharing this deep, rich information that you have with all of us. We're also lucky that you do that. Thank you so much. Thank you so much for that, sir.
You bet.
To all the attendees, thank you so much for tuning in tonight, and hope you can join us next week when we have 2 webinars, one on Tuesday night, one on Wednesday. Have a great night, everybody.
Good night, everybody.